Okay, I have started the recording, and I am bound to announce that, just so you know. As you know, going forwards, especially looking at the fall semester, we have to have great clarity when we're recording and when we're not recording. So, yep, just want to mention that. And there's a time and a place for the recording, right? Typically during discussion sections, office hours, we do not record the meeting because we want to emphasize that you should feel free to verbalize any question you may have and not have to worry that your question was recorded. All right. So, and by the same token, I do not save the text log that is produced by Zoom for the chat. Right? Don't record it. Okay. So today we've got Thursday, the 30th. Obviously tomorrow we have an exam. Let's revisit this topic we talked about at the end of our last meeting. We talked about the double pendulum. We set up the Lagrangian exactly. So much of this calculation was exact. And we computed the kinetic energy. Some effort was required. But in doing this, we exercised our foundation skills in setting up the Lagrangian, computing the kinetic energy in an inertial frame, right? And we'll revisit some of those foundation concepts today, again, in our calculations, okay? So we had the exact Lagrangian. Unfortunately, the resulting differential equations are too difficult to solve. No surprise there because we've talked about the fact that this is a chaotic system. And when we study chapter 12, we'll be talking about this as one of the prime examples. It's a 2-degree of freedom system that exhibits chaos. Now, if we do the small angle approximation, okay, we're going to do the small angle approximation. We go to second order in the Lagrangian in our variables, the two angles, and then the two time derivative, right, the q dots. In general, we speak of q's and q dots. So now these are phi dots. Then we got the equations of motion, and we wrote them in this form. This is the form that we really like. In chapter 11, we study oscillations near equilibrium, and we have these nice matrices. A special example, a special case, we mentioned this at the very end of our last lecture. If the two masses are equal and the lengths of the two rods are equal, then you have this nice structure. Omega 1 is this is a numerical constant, the square root of 2 minus the square root of 2, wonderful constant, times this omega naught, which is the usual square root of g over L. This is a very convenient symbol, this omega naught. Even though we do not have a mode that swings with that frequency, it's useful to define this. And of course, that's the frequency. If you were in the laboratory, get out your toolbox and remove this lower pendulum. That's the frequency that you would have here for small oscillations. As you know, for large oscillations, the frequency is different. Okay, and for truly large amplitudes, the frequency goes to 0, right? The period goes to infinity. That's something we studied at the beginning of our course. Okay, so we have these frequencies. Let's talk about these were the two frequencies. Here we go. Let's visualize the behavior of the system, the actual solution. What does that look like? Okay, and these are the pictures that go with the two modes. So in this mode here, the angle phi 2, now let the record show, this is greatly exaggerated. Remember, the basic premise of this calculation is that we're going to look at small angles. Here, the angles are really quite extraordinary, right? That's about a 30-degree angle, and this one's about more than 45 degrees away from the vertical, phi 2. Okay. For this mode, and again, thinking of the small angles, it's true for all time that phi 2 is the square root of 2 times phi 1. That is to say, the amplitude for this mode all right. You have an arbitrary multiplier Okay, so that vector right there, that's at the heart of this formula. It's a vector, if you wrote it in the familiar notation with ordered, in this case, ordered pairs, you would write 1 comma root 2. Here we've written it as a column vector, so it's just written as a 2 by 1 matrix. There's a 1 up here and there's a root 2 down there. And for this one, again, let's emphasize it's true for all time. If you have this pure mode, then for any value of the time t, phi 2 is minus 1.4, etc., times phi 1. And that's what I made an effort to show that here. For small angles, you can eyeball this angle here. The sine of the angle is roughly equal to the angle for the small angle. And then I go from here, I'm imagining a reference line straight down, and then I go 1.4 times that to the left. So this dot is about 40% to the left of the line, as this dot is to the right. You know, let's appreciate these nice details that are part of the problem. And of course, this oscillates back and forth. The two masses are 180 degrees out of phase in terms of their time evolution. Here's the eigenvector. Once again, this generalized eigenvalue problem. Okay. Yep, so that's, again, a summary, and it's nice to have this concrete example. This is some apparatus you can and should build at home. You know, there's really no excuse. Okay, I'm kind of guilt tripping you a little bit, but at least in principle, we could imagine building this. You could just get 2 pieces of dental floss, right? And 2 objects that are small and massive. Those are abundantly available. And then you can arrange for this. And you can convince yourself, this one is kind of swinging back and forth. Last time you went horseback riding, you can see a similar behavior. If you got a horse with a long tail, my sister would know what those things are called, I don't know. Anyways, when they swing them back and forth, you have this kind of behavior. This one here, this is a little more complicated, but again, you can demonstrate this in your home laboratory. And experimental physics is really important, right? So it's good to get out there and do this stuff. All right, so now let's look at the general case. We're going to bring in, again, some of the foundation concepts from our studies of Lagrangian mechanics, because you know what? The final exam is sneaking up on us. Guess what is 2 weeks from today? Yep, that's our final exam. So of course, after we get through this midterm, I'll start broadcasting information about the final exam. And of course, we're going to need to know our Lagrangian mechanics. Okay, so here we go. We're going to talk about a Lagrangian approach. And I've drawn this big horizontal dividing line to indicate this is now a new section. It's not directly related to this previous discussion for the double pendulum. We're now going to talk about a very general case. Okay, the general case, we're going to assume this is our usual notation, right? Lowercase n tells us the number of degrees of freedom. So we're going to assume n degrees of freedom. We'll assume it's holonomic. Okay, and you know what that means. We can write down a formula. Good old equation 734. We know how important this equation is. 734. You're pretty much guaranteed to see this on the final exam. 734. Okay. Notice no explicit time dependence. Okay, and again, these are the generalized coordinates. We're very familiar with this notation, Q1 through Qn, generalized coordinates. Let's appreciate the constructions, right? So it's the existence of this function, right? For any given problem, whether it's a double pendulum or, on the homework, we'll do something more sophisticated. We're going to have something with 3 degrees of freedom. So that's kind of the increased level of sophistication there. And of course, there will be different choices of generalized coordinates available to you. So we'll consider the various choices. But if you have a rigid bar, so let's pretend this pen, obviously rigid. In the photo I posted, which was on the cover sheet of a recent lecture, I upload the lecture notes as well. There's a photograph which I look at longingly. It's the view from my office window. And at that time, I constructed this apparatus where the metal bar is actually an extension bar for a socket wrench set. Okay, sometimes you need an extension bar. And so that's a very massive solid metal bar. And then it's suspended by these very thin threads. We'll assume those are massless. And so then the question becomes, what kind of frequencies will you see? And it would be a really fun experiment to take some data. You give it an arbitrary initial displacement away from equilibrium, and then Fourier transform the data. You should see 3 spikes, right? Because there are 3 eigenmodes. And if you start the system in an arbitrary state, all 3 modes should be excited. And those 3 frequencies should be visible. That'd be a great, that's on my to-do list, especially since we're bringing Python into this whole thing. That's on the to-do list. Okay, so this is quite general. We know we must compute the total time derivative. All right, so for any given problem, this is, you could say this is a template. All right, the notation, again, this is the notation that's in the book. We're saying R alpha equals R alpha of. It's kind of redundant notation that doesn't carry an immediate statement other than to convey the dependence, right? The relationship between the variables. The statement that particle number alpha, remember alpha is the particle label index, the position in a 3-dimensional space, inertial space, inertial reference frame, is a function of these coordinates. And you can write this down for the double pendulum or any other problem, right? The double pendulum would be a really nice example where you would use vector addition, right? You have your 2 angles, you have a reference point here. Your first angle enables you to write down the location of this point as a function of the angle, and then you do a vector addition to get here, okay? So in this sense, this is what you would see on a typical exam problem. You can compute the location of particle number 2 here as a function of the 2 generalized coordinates, phi1 and phi2. And it's accomplished using a vector addition, very powerful tool. Okay, so quite generally, we can differentiate to get the velocities. This dot indicates the total time derivative, not the partial time derivative. The partial time derivative would be 0 because there's no explicit occurrence of the time t here. The total time derivative, and that means we now think of Q1 as a function of time all the way up to Qn. These are functions of time. Each one is its own unique function of time. The chain rule in a higher dimensional context tells us what to do. Right? And this chain rule comes immediately from the definition of the derivative. If you write down the definition of what it means to differentiate this function with respect to the time t, then you will arrive at this formula, because you'll do a higher dimensional Taylor series expansion and pick off the order 1 terms, right, the linear terms. And what you will get okay, so we have to be very cognizant of what's going on here. The first line here indicates that there's a functional relationship. Here in the second line, one of the objects that occurs is a partial derivative. So that's a partial derivative of this function thought of as a function of these independent variables Q1 through Qn. If you have that mathematical setting, then it is meaningful to talk about this partial derivative, okay? After you compute the partial derivative, then you insert these n functions. Now they are functions of time t. This resulting object is a function of the time t. This q dot I is a function of the time t. And this, via functional composition, right? After you compute the partial derivative, then you insert these functions of time. It too becomes a function of time. This whole thing is one grand function of time. All right. And of course, this enables us to compute the kinetic energy. This is a calculation we did at the beginning of the course, but it's good to review this because these topics are considered amongst the more difficult topics when you have this kind of a calculation where sometimes we think of this as a function of independent variables. And then for this construction, we've inserted the so-called orbit of the system. That's when we insert actual values, functions of time here for these q1 through qn variables. Okay, having said that, we can compute the kinetic energy. There's a contribution from each of the particles. That's the sum on alpha. It's understood that the sum on alpha goes from 1 to capital N. Capital N is the number of particles. Okay, mass. And of course, this is notation only for the initiated. Who else would think of this kind of crazy notation? These two dots indicate time differentiation, the total time derivative. This dot indicates the vector dot product. As long as everyone's clear, then there are no hard feelings on this. That's our notation. Okay, as you know, each of these now, we're going to insert this formula. The index I here is a dummy index, and I've emphasized that by explicitly writing down the limits of the sum. It's similar to when you have an integral. Suppose you have a one-dimensional integral. If the two endpoints are fixed, kind of constant objects, then the variable of integration is a dummy variable. It's gone after you do the integral. You're basically sampling a function at a bunch of values and adding it up, and through the miracles of calculus, going to the limit, where you do this with exquisitely a fine subdivision. Okay, so now we'll plug in, as you know, we did this earlier in the course. Okay, so here we go with this sum. Okay, and now, of course, we have a dot product here. And now it's really the same object, but we're going to use a different index for the summation because we're going to rearrange the terms. And it's important to appreciate these are two independent sums. If you like, you can dispense with this index j and this index k and imagine writing out this partial with alpha equal to 1 plus another term where alpha is 2 plus, and you'd write dot, 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 all the way up to the last term where this index alpha is capital N. Okay, so this parentheses here would include that kind of a sum written out, and then you must include a dot, dot, dot because we have an arbitrary number of terms. And again, this next parenthesis would be exactly the same thing then. Partial R. Okay, so the structure that emerges, this is the important thing to us. This is a quadratic form, right? If you look at how the resulting object depends on these velocities, these are generalized velocities, right? These q dots. Every term is homogeneous second order. There are some terms where you have a q dot variable raised to the second power, and then there are other terms where you have a product of two distinct q dots. But all those terms are second order in these velocities. And so we like to write it like this. Okay. This is something we've seen before, but now we really want to be clear that this matrix here is computed in the following way. Okay, that was the first partial. That partial derivative, of course, it's still a vector. We form the dot product. Okay, so this object here, again, we have a very clear prescription. It's the existence of this function here. For any one of the particles, right, you have this function. The existence of that function allows you to do this construction. And here's a clear prescription for how you compute this matrix. After you carry out the sum over the particles, then the resulting object, and this alpha is a dummy index, the resulting object does not have any reference to an index alpha. You do have these two free indices, the j and the k. Okay, and it's important to emphasize here that this resulting thing is a function of the q's, right? So this is a function okay, it's a function of our generalized variables. So here's what we're going to do. Remember, our goal is to study the oscillations, the motion of a system near equilibrium in this very general context. We could do some sort of triple pendulum. You could even, why stop there? Have a quadruple pendulum. And in the limit, you would have essentially a chain. Think about all the interesting physics you can do if you have a chain suspended from the ceiling. This is something with a linear mass density. And think about the different modes there. All right, so fascinating stuff. What we're going to do for the small angle approximation, right? The analogous thing that we did here for the small angle approximation. Right, the emphasis here is that this AJK thing is a function of the generalized coordinates. Now for our analysis for the small oscillations about equilibrium, here we go. We're going to define the mass matrix, okay, as follows. And here's the crucial thing. We take this object, this matrix AJK, which is a function of the q's. We evaluate it at the equilibrium location. Okay. Now notice what we've done here. I'll indicate with the pen as a pointer. We stated verbally that we are going to evaluate this matrix A at the equilibrium location. So there are two different ways you can look at this. You can look at this as literally saying we're going to plug in zeros for all the q's. You know, you can accomplish that because of the very nature of generalized coordinates. Suppose you do have some generalized coordinates where the equilibrium is at some non-zero location of the q's. That's fine. You can define new generalized coordinates, which are equal to the old generalized coordinates plus a constant offset. So you can always arrange that the equilibrium is at 0 for all your q's. Okay, so it's in that sense that we have a 0 here, 0 for all the q's. Alternatively, you can think of the 0 as kind of a cursive 0, cursive capital O, indicating the origin. Again, it's fully equivalent to saying we've identified some equilibrium in the Q space, right, the configuration space, and we evaluate this matrix at equilibrium. So let's write that here. Okay. The notation here indicates, as I said, simply by writing 0 here, it's understood you're going to evaluate this matrix at the equilibrium location. So for the double pendulum, it literally was a 0 for both of those two angles, phi 1 and phi 2. Okay. And then you get this matrix, and this is precisely the mass matrix that we determined earlier. Okay, so that's our definition. The other one is our spring constant matrix, our K matrix. Here we have a very clear prescription. You do a second order Taylor series expansion. Okay. And we'll write it like this. Okay. You know we like to take those variables. Sometimes we write Q1 dot 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 Qn. That's our collection of generalized coordinates. And we like to arrange these into a column vector, and then we use this notation. This need not be a 3-component vector. It could be 15 or arbitrary number. This is our collection of generalized coordinates. Again, lowercase n is the number of generalized coordinates. Okay. So while we're on the subject, notice the structure here. This kinetic energy, again, we have this summation, and we've proven that this matrix is symmetric. So this has the structure right? You can write this as the Q vector, and there are dots, right? So we have the Q vector dot transpose, then you have this A matrix, and then you have the Q vector dot. So here we've used the summation notation, the J and K summation. It's fully equivalent to use matrix multiplication. And this is, again, standard matrix multiplication. If you have this rectangular matrix, remember this is a 1 by n rectangular matrix. This is an n by n square matrix, special case of rectangular matrix. And this is an n by 1 rectangular matrix. Standard matrix multiplication gives you precisely this expression for the result. And the result is a 1 by 1 matrix. Of course, the kinetic energy is a scalar. That's exactly what we expect. Okay, let's consider a second order expansion of the potential about the equilibrium. All right. So using the same notation, we know the leading term is the constant term, the value of the potential at the equilibrium, and we'll use the same notational convention as writing 0. Simply writing 0 is an indication that we're going to evaluate this at the equilibrium location. And again, if you like, you can simply shift your generalized coordinates so that they literally are 0. Each and every one is 0 at the equilibrium. Okay, so then a higher dimensional Taylor expansion would next, it would have a bunch of linear terms, the first order terms. But because this is an equilibrium, all those are 0. All the first order terms are 0. If they were not 0, it means you're not at equilibrium. There's some sort of force on the system. So this 0 is kind of a placeholder to remind us that in principle you do have first order terms here in this generalized expansion. And now comes the fun part. Okay, so what have we done here? Again, it's a second order expansion. And even if you have just 1 degree of freedom, which is perfectly okay, if lowercase n is 1, then there's no need for these sums because these indices, j and k, just go from 1 to 1. That means they have just one value, and that's 1. You see that there must be a factor of 1/2 here, because even for the case of 1 degree of freedom, you see the structure is 1/2, then there's this constant, and then you have Q1 times Q1. Admittedly, I squeezed it in there, but this is the QJ. QJ. All right. And because of the equality of mixed partial derivatives, this matrix is going to be symmetric as well. So this is our K matrix. I might as well write it like this. That prefactor, which of course you evaluate at this location, that's true for any sort of Taylor series expansion. you evaluate all these derivatives at the point about which you're doing the expansion. So it's understood that this derivative is evaluated at this point. So this collection, again, this is a square array of numbers. This is what we're going to call the K. Right? So this is K, capital K. Okay, so you see what has emerged here. We have these two matrices which are fundamental to the problem, the capital M matrix, the mass matrix, and the capital K matrix, that's kind of the spring constant matrix. All right. Again, you can recognize the familiar structure of a quadratic form. This construction with the sum over little j and little k, again, has this structure as a matrix product. Okay. The crucial takeaway message here is we worked out a Lagrangian. Okay. This is the exact kinetic energy. Notice we go to second order here. We have not made any sort of approximation. This is a homogeneous second order polynomial in the q dots. The exact form has a functional dependence. This capital A sub jk is a function of the coordinates. Right? Now the crucial thing is if we're going to examine oscillations near equilibrium, then we're going to show you want to define this capital M matrix to equal this thing evaluated at the equilibrium, not near the equilibrium. It's evaluated exactly at the equilibrium. Furthermore, you evaluate these partial derivatives at the equilibrium. Okay. In doing so, we get these two square matrices, the capital M matrix and the capital K matrix. All right, so let's take a moment to emphasize the structure that has emerged here. Okay, so the crucial thing is, remember we have the concept of the classical state. Okay, the classical state of the system, right? This encapsulates enough information to determine the subsequent evolution of the system. That means you have both position and velocity information. So the classical state, you've got Q1 through Qn. You have information about the configuration. Okay. So these numbers, there are two n numbers here. You could say two n parameters. Those two n parameters, that's the number of parameters, they determine the classical state. Okay. Now, the configuration is determined by these numbers. All right. So the configuration, in other words, if you take a photograph of the apparatus, an ideal photograph that takes just one instant to register, then that is equivalent to this information here, the Q1 through Qn. Again, the assumption is the existence of this function here, right? If you have this function and knowledge of these coordinates, then you can determine the location of every particle in space in the inertial frame. Okay, so that's the configuration. Now the classical state carries more information, in some sense twice as much information, because you need Q1 through Qn, you need Q1 dot through Qn dot, and that's just the way nature is, right? You need the positions and velocities that determines the evolution of the system, right? Because Newton's second law tells you that the acceleration, it's determined by the force, and if the force is determined by these parameters, then you have an equation of motion that determines the evolution of the system. Okay, so let's integrate this with what we have said here. Okay, let's get this a little more organized here. The pens keep rolling onto the writing surface here. All right, the crucial thing is, right, this mass matrix is evaluated at this configuration, okay? You do this calculation and then you evaluate at this configuration. You do not evaluate at a nearby configuration. You evaluate it exactly at this configuration. All right, that's the very important message here. And it's really a very useful message for solving problems. For all these different problems, for example, at the end of the chapter, you see a lot of interesting problems. To determine the mass matrix, you just need the kinetic energy, right? And let's emphasize that here. To determine the mass matrix, you compute the kinetic energy, right? Now, to get the kinetic energy, you need all this information, right? T is our symbol for the kinetic energy. Let's scoot this back out of the way. And this, all right, so this is kind of the big picture. To compute the kinetic energy in general, and you saw this for the double pendulum, we needed to know about the q dots. In that case, we had a phi1 dot, a phi2 dot. But there was also, when we computed the exact kinetic energy, there was a dependence on the angles. In that case, it depended on the difference between the two angles. So that's an example of this general state of affairs. To compute the kinetic energy, in general, you need to know all these numbers. Okay. For the potential energy, you just need the q's. All right. Now, bring in chapter 11. Our analysis of the behavior of systems near equilibrium. What you must do is compute the kinetic energy for the following classical state. All right. So here's the prescription for success. And this is a big time saver. So you compute the kinetic energy for this classical state. Okay. And now let's specify the classical state. There are two things we must specify. The q's exactly equal to the equilibrium position. Okay, so this is the situation for chapter 11. And so this is a way to summarize what we're doing here. To examine the oscillations of the system about an equilibrium location, you do this calculation, and this is the good news. The Q, right, the configuration is exactly equal to the equilibrium configuration. You do not have to consider a nearby configuration. So for example, if you're studying the pendulum, the simple pendulum, where you have a single mass hanging from a string, then you compute the kinetic energy when the thing is exactly vertical and when the velocity is arbitrary. You write down a formula for that. So you see how it's a big time saver that the configuration is exactly equal to the equilibrium configuration. Okay. So based on this, you get the mass matrix. All right. Then here, you do have to consider a configuration near the equilibrium. So compute U. Remember, it's a function only of the configuration. For a configuration approximately equal to the equilibrium. Okay, so again, for chapter 11, this is what we're doing. And this is what must be emphasized. For the kinetic energy, you have the Q, right? The configuration is exactly equal to the equilibrium configuration. The velocities are arbitrary. You figure out the kinetic energy, write down a formula, you get this mass matrix. For this one, you have to go to second order. So you compute the potential energy for a Q vector, a configuration near the equilibrium, and go to second order. And then you will get your K matrix. And once you get the K matrix, then you're in the wonderful world of abstract mathematics with matrices, right? You have two matrices, and we know how to solve the generalized eigenvalue problem. So the rest of the course is just a walk in the park, so to speak. I don't mean to belittle the difficulty there, but at that point, we've distilled the problem to that of the generalized eigenvalue problem. We have our two matrices, and we must compute eigenvectors and eigenfrequencies. Okay, so that's the general approach. And let's check on our time. Okay, so we do have time to make a few remarks. Let's make some remarks that will pull together quite a few chapters. Think about all the fun we had computing the tides. We can see how that figures into this. It fits right into this discussion here, all right? So suppose you have, we can make the following statement. Consider, okay, as an example, let's suppose you have a potential energy. It's a function of x, y, and z. This R vector, of course, that denotes our variables x, y, and z. So suppose you have the case, as we often do, that this is some function of the distance from the origin, right? You know, when we started chapter 8, we started talking about central forces, and we quickly proved that the potential energy is only a function of your distance to the origin, okay? Well, there's a little shortcut you can do here. If it's a function of the distance to the origin, then equivalently, you can say it's a function of the square of the distance. That serves to remove a square root, which helps to clean up things. So what we're saying here is, if you have a problem where the potential energy, this is our notation for a scalar field, right? It's a scalar, the potential measured in joules, and it's a function of position, right? If you have a three-dimensional space, it's some arbitrary function of position. This includes our calculation with the tides at the beginning of chapter 9, okay? Some arbitrary function in here, we've chosen to write it like this. We could have put a square root around x squared plus y squared plus z squared. Then it would be a function of the distance to the origin. It's convenient to just define it this way. It means there's a slight change in the definition of f. Now it's a function of this thing, which has dimensions of meters squared, okay? If that's true, we can compute this Taylor series expansion to second order about an arbitrary point, okay? And this is what we saw in the tides. We had to do that. Okay, so we're given this function, and suppose we have some R naught. Okay, so this particular statement will be useful anytime you have a problem where there are multiple forces. Of course, we ask that they're conservative. Notice that if you have a spring attached to the origin, one end of the spring is attached to the origin, the other end of the spring is attached to a particle. An ideal Hooke's law spring would have a force proportional to your distance from the origin. A real spring, of course, has some sort of rest length. If you remove the spring from the apparatus, it doesn't become vanishingly small. It has some natural rest length. So that's a case where you would have an R naught. Okay, so then we can do this Taylor series expansion. Here's the interesting result. Okay, we won't be going through all the details of the calculation here, but we just want to appreciate the structure. Anytime you do a Taylor series expansion, first thing you do is you state the leading term. This is the value of the function at the point about which you're expanding. So we're going to do a Taylor series expansion about this point. Okay, so what's the linear term? Turns out this is 2f prime, right? Evaluated at this point here, and the value would be the R naught squared, right? R naught squared is x squared plus y squared plus z squared at the equilibrium. All right. And then we have the R naught vector dotted into, we'll call this R minus R naught. Okay, so that's the linear term. Now the quadratic term, let's start talking about the quadratic terms. Here there's a couple contributions. Okay, that's one term. And then there's another term with a factor of 2, and it's a double prime. And here we have a different structure. It's only the radial component. Okay, so again, for today's lecture, let's not go through the proof. It requires a little bit of effort. Let's just appreciate the structure that we do have. Well, we do not have our red pen. We have the 0th order term. So that's the 0th order. This is the 1st order. Okay, it's 1st order, and this quantity in parentheses here. This is the excursion. It's a vector excursion, a vector displacement away from this point, the reference point. R naught is the reference point. So that's 1st order. Here we go, 2nd order. Okay, so it's interesting that the 2nd order terms take this form. Notice there's one contribution where you have 1st order differentiation of f, and now this is the square of the vector displacement away from the reference point. There's another term where you have the 2nd derivative, of course evaluated at this reference point. And now notice the structure with the dot product. We have this vector excursion, the vector displacement away from the reference point here, dotted into the radial direction, that quantity squared. And then there are 3rd and higher order terms. If you like, you can grind them out. It would be quite an enterprise. But this is useful for a variety of problems. Again, anytime you have a problem with a spring, and we'll have a bunch of problems with springs, some of them with a non-zero rest length. Okay, you can use this result. The problem with the tides. Okay. So for example, for the tides, when we looked at the tides, at the beginning of chapter 9, right, the familiar Newtonian gravitational potential. Okay, so that's certainly true. Let's observe this symbol x squared plus y squared plus z squared. We need a name for it, and observe it's measured in square meters. So let's use A for area. So we can say f of A equals minus GMM over root A. So there you have it. This is a nice example of an f function for one of these problems, just to make this more concrete. And so we need f prime. Well, that's going to be a constant times a to the minus 3 halves. F double prime, that's a constant times a to the minus 5 halves. So those results that we had for the tides, right? We needed to know about these equipotential surfaces. Again, you can get that directly from this formula. Okay, so our point here, the takeaway message from this discussion is chapter 11. Let's really celebrate these results. And one of the most useful things is here. Often, over the years, what happens, we see students when they work on these problems and they're looking at the kinetic energy, they consider a point where we're near the equilibrium configuration and they compute the kinetic energy there. That creates a lot of extra work because it turns out you can have Q exactly equal to the equilibrium configuration. So for example, for the double pendulum, the equilibrium configuration where both of these pendula are hanging straight down. The problem is much simpler in that case because the two velocity vectors of the particles are perfectly horizontal. And this is completely rigorous. So for that double pendulum case, now you're looking at a classical state where the pendulum, the configuration is perfectly vertical. The two velocity vectors of the particles are perfectly horizontal. There's no contradiction there. That's completely true when the pendulum is perfectly vertical. And then you can compute the kinetic energy with ease. You don't have to worry about these annoying angles, right? So again, this is a huge time saver that to properly implement this, it will save you quite a bit of time. Here for the potential, you do have to go out to second order. And I thought I'd mention this result. This is optional, but sometimes it's a big time saver. Okay. So what we can do now is we have a Lagrangian. And we know what you should do. If you have a Lagrangian, start computing partial derivatives. All right, so let's appreciate that we do have a Lagrangian here. Okay. This is our usual formula, Lagrangian T minus U. So this is a 1/2. The kinetic energy, we know it's this bilinear form, right? So we've got our Q vector dot transpose. We got the mass matrix. Okay. Potential energy. Okay. So now within the Lagrangian formulation, we must compute some partial derivatives. Again, let's be clear, there's no explicit time dependence here. So this is a Lagrangian. Okay. This is the structure of the Lagrangian. Again, the Q vector embodies Q1 through Qn, and the Q dot vector is a shorthand for Q1 dot through Qn dot. All right, so there's our Lagrangian. We know there are some partial derivatives to be computed, okay? The good news is there's no Q dependence here. The mass matrix is simply an array of constants. So when we compute derivatives with respect to the coordinates, we must focus on this term here. All right, so the crucial thing then is the partial derivative okay. Right, again, this business here, that's the potential energy, capital U. We must differentiate with respect to one of the coordinates. So the notation here, Q sub I, is telling us we're going to compute a partial derivative with respect to one of the coordinates. This I is called a free index. It represents any one of the indices. It could be 1, could be anything in between, all the way up to lowercase n. All right. So the structure, we won't go through the details too much here, but the structure is the following. We're going to differentiate this. Okay. So we're justified in doing this, right? Because all of these coefficients k, they're constants, right? Once you've done that Taylor series expansion, these are certain derivatives evaluated at the equilibrium configuration. So those are simply constants. So the question becomes, what is going on with this fundamental object here? What can we say about this thing here? It's the partial derivative with respect to coordinate qi of the product qj, qk. And j could equal k, or they could be distinct. Both of those are completely acceptable because this notation indicates we're going to have a sum over all allowed values. So j and k go from 1 to n independently. Okay. And yeah, there are times where j equals k. There are times where they're both, actually, there's just one time where they're both 1. It's the first term in the sum. Okay, so what's this derivative? Okay, so, okay, we do have a cat situation, just a second. Okay, so, yep, that was a senior citizen cat, and if they need to use litter box, do not delay. So we're going to use the product rule, right? We're computing the derivative of a product, so there are two terms. The first term is where this differential operator acts upon the first factor. That's going to give us a Kronecker delta ij, right? Because these are independent variables. So if I is distinct from j, you have a 0. If I is equal to j, it's 1. That's precisely the Kronecker delta. Then we copy over the second factor. Okay. And then similar story here. We copy over the first factor. And then we differentiate the second factor. Okay, etc. So what we've done here is we've evaluated the derivative. This is the general expression now for the derivative with respect to one of the coordinates, and we're differentiating a product. We have this nice term. Then we can go ahead and carry out the sum, okay? And the upshot is we'll skip a bunch of, this gives you a feeling for what the calculation is like. We'll skip a bunch of the details. This is equal to a component of the product of two matrices. The first one is a square matrix, or K matrix, and the second one is a rectangular matrix. It's an n by 1 matrix. You can also call it a column vector. But here, we're viewing it as a matrix product. The result is a column vector, and we've got the ith component. Okay, there's a very similar calculation for the kinetic energy. As you know, we must compute derivatives of the Lagrangian partial derivatives with respect to q dots, and they only occur here in the first term. Okay, so it's a very similar story. The partial derivative of the kinetic energy with respect to one of the q dot I, one of the q dots, and we'll look at q dot I, exact same structure. The structure is identical here. You form a matrix product. We have our mass matrix, which at this point is a bunch of constants, times the vector, column vector, qi column vector. The resulting object is a column vector, and we're going to select item number I. So the component I, the ith component. Okay, now, so this guy here, this guy's a known troublemaker. I'm going to stick him on the document camera. He's sniffing the document camera. Can we get him on the camera? I don't know. Just thought that might liven it up a bit. Now, his only excuse is he's a known troublemaker. Okay, now they're both out of here. Evidently, nap time is over. So yeah, having established this structure, we have a wonderful conclusion. And it's basically the conclusion we were seeking the whole time. The mass matrix times the q double dot vector. We get the second order derivatives when we complete the program of the Euler-Lagrange formalism. It asks us to compute a total time derivative of essentially this, right? Because the Lagrangian differentiator with respect to this variable is equal to the kinetic energy for this problem, differentiated like so. And we do get this q vector double dot. We get our minus sign, and okay. So this is the conclusion. We've now established a very general framework, and it will serve you well. All right. Remember the main points here, that you can calculate these matrices, right? The key is to calculate these two matrices. We've got the M matrix, the K matrix, and this is a prescription for success. All right. So that's then the general framework for these problems. Tomorrow I will be posting homework assignment number 9. It's going to be due Tuesday, and we'll have a lot of fun on homework assignment number 9, examining some fascinating systems. So that's due Tuesday next week, and that's the 7th week of our 8-week session here. So you see, it's really an extraordinary thing to teach Physics 105 and do this in 8 weeks, right? Now we've reached a major point in the book. This is kind of what Taylor calls an intermission. We've covered all of the major topics. The following chapters, so that's chapter 12, chapter 13, etc., Taylor basically gives you permission to do them in any order you like. So we're actually going to skip chapter 12 for now. We'll come back to 12 later. We're going to go into chapter 13. All right. So here we go, chapter 13, the Hamiltonian formulation of mechanics. Okay. So the Hamiltonian formulation of mechanics, this is yet another formulation of mechanics. Why would we need to do this? We already had Newton's laws, perfectly good formulation of mechanics. So then we had this alternative formulation, the Lagrangian formulation. Okay. Why do we need yet another formulation? So here we go, chapter 13. Okay, there are several things to be said here. You know, I spent several years working, I guess it was, what was it, 2010 through 2013, at Lawrence Berkeley National Laboratory, and we have a state-of-the-art, you know, 3rd generation synchrotron. And I've mentioned, you know, a user population, 2,000 users a year go there to do ultra-fast X-ray science. The machine produces these bursts of X-rays that are perfect for all kinds of applications. You've got people working on photosynthesis, people working on combustion, mapping out proteins, et cetera, and so forth. So ultra-fast X-ray science, again, a fascinating, fascinating business. Obviously, they have conferences, et cetera, and so forth. And Hamiltonian mechanics, right, important for the design of the machine, right? You have typically a nanocoulomb, a couple billion electrons. A couple billion electrons, and one speaks of a bunch. So they're kind of grouped together in a bunch, and they go zooming around this machine at nearly the speed of light. And we'd like to increase the density, right? The machine produces better quality X-rays in the sense of brightness, better quality bursts of X-rays. If you can get these electrons closer together, not only in physical space, but in momentum space. So you see, we have to extend our notions of density. In the Hamiltonian formulation, we have Louisville's theorem, and there's really no equivalent statement in the Lagrangian formulation. Okay, talking about densities of basically, thinking of these electrons, densities in phase space. And typically on a weekly basis, we would meet with the team of physicists who devote their lives to the, you know, the physics end of the machine, keeping the machine running and improving the performance. And they plan out these wonderful upgrades and install really impressive quadrupole magnets and higher, not only quadrupoles, you've got the dipole magnets, the quadrupoles, but higher order poles to improve the brightness, right? So Hamiltonian mechanics, they do talk in the language of Hamiltonian mechanics because of the notion of the phase space density. So one of the main theorems here will be Louisville's theorem. And again, there's no real analogy in the world of Lagrangian mechanics. So we'll talk about some other formulations. There are various statements we'll make about how you can capitalize on symmetries. And we know the Lagrangian formulation has a lot of powerful statements about symmetries. Okay, and then we're going to get to the subject of canonical transformations. Okay, so let's begin by just describing what is Hamiltonian mechanics, and then we'll, again, perhaps a little bit on the defensive, try to explain why we need another formulation of mechanics. Right? Obviously, we're wide open to criticism here that this is just too much abstract theory. But here we go. First, let's explain what's going on with Hamiltonian mechanics. So the prescription, thinking way back to chapter 7, we did compute a Hamiltonian. Remember, we start with a Lagrangian. Okay. In chapter 7, we computed a Hamiltonian, but we still express it in terms of the Q's and the Q dots. Now we're going to do something a little different. Okay, so we're going to start with Lagrangian. We're going to compute the partial derivative with respect to the Qi dot. You know, this is necessary for the Lagrangian formulation. This function, let the record show, this function is again, in general, a function of all these variables. So it's a function of Q1 through Qn, Q1 dot. Okay, so this is very important when you have a function of multiple variables. If you compute a partial derivative, the resulting function is again a function of those several variables. We define this to be lowercase p sub I. This generalized momentum. That's a familiar concept from chapter 7, right? In the Hamiltonian, as you know from chapter 7, that's a capital cursive H. I like to put parentheses around this to indicate first you evaluate the sum, then you subtract one copy of the Lagrangian. Okay. Without the parentheses, there could be a huge misunderstanding that people think it's pi Qi dot minus the Lagrangian, sum that over I. Then you would have n copies of the Lagrangian. So well, this is a little more clear. Okay. Now here's the crucial thing. We're going to solve, right? Solve for the Qi dots. Now remember, we've been emphasizing all summer long that kind of at the heart of classical mechanics is keeping track of all these different variables and what is thought of as a function of what other variables. We're going to solve for Qi dot okay, and this is coming from this, let's put an arrow like so. Having established this, and remember you have a collection of equations here, this I is a free index. So we have one equation for I equals 1, another equation for I equals 2, etc., all the way up to I equals little n. We have a bunch of equations, n of them, and we can solve for the Q. There are n of these unknowns. We would like to solve for these velocities, generalized velocities. So in principle, that's an algebra problem, right? For any given problem, maybe you're working on a simple harmonic oscillator or some sort of double pendulum or what have you. The existence of this function here, right? And again, this is some function of the Q's and the Q dots means, and since you have n equations and n unknowns, you can solve for these Q's as a function of the Q's and P's. Having done that, you can insert the solution into this equation here. And what do you get? You get a Hamiltonian that's a function of the Q's and P's. Okay, so for the Hamiltonian formulation, uh, we're going to carry out this prescription. And it's now the existence of this function. The space of Q and P is called phase space. Right? We've been careful to keep a distinction here between the classical state space. Remember that Q's and the Q dots, we talk about the classical state. Of course, it's fully equivalent here to the so-called phase space, but the terminology that is used in Hamiltonian mechanics is one speaks of phase space. So you have all these Q's and P's. Right? The same remarks apply. If you know the values of the Q's and P's, that's enough information to determine the subsequent evolution of the system, right? Because it's equivalent to knowing all the Q's and all the Q dots, the velocities. Okay, let's go through. So this is kind of the abstract setup. Let's go through some examples. This will help to clarify the situation. Free particle 1D. All right, this is pretty much the simplest example you could think of. Free particle. So that means the potential is a constant. Might as well set it to 0. And one-dimensional motion. So this is the ultimate in simplicity, right? Pretty much there is no simpler mechanics problem. We have a Lagrangian. Right. So Q is our coordinate along the axis. Sometimes we like to call it X. It's fully equivalent to just call it Q. The momentum, right? The next order of business, compute the momentum. So we have, in this case, since there's 1 degree of freedom, we do not need these subscripts. Let's just get rid of them. It's one more thing we don't have to worry about. So this lowercase p is our one instance of one of these little p sub I, the momentum. We must compute a partial derivative. All right, we're getting the m q dot. Next step, we must solve for q dot. So that's easy, we just divide by m. So in this case, things are looking pretty good for us. It's 1 over m times p, okay? And then write out the Hamiltonian. It is a case where you have the q dot, right, times the p, and then you subtract off the Lagrangian. So you end up with, there's a little bit of algebra here, right? But let's just get right to the punchline here. The Hamiltonian is p squared, that's a lowercase p over 2m. Okay. So it's well known that if you have a free particle 1D, then the total mechanical energy is just p squared over 2m. All right. But it was useful just to see how this is an example of our general prescription. Okay. All right. So let's do something a little more dramatic. Let's look at the simple harmonic oscillator. Okay, simple harmonic oscillator. When we write the SHO like that, simple harmonic oscillator. So our Lagrangian is that kinetic energy term we just investigated. And then we subtract the potential energy. The momentum, same expression as before. I'll skip some algebra. We get a Hamiltonian p squared over 2m plus a 1/2. Here's a lowercase k. Okay. So again, this is a case where the Hamiltonian is, as we know from chapter 7, the total mechanical energy. All right. Now let's draw a picture of the phase space for this problem. And in physics, you typically draw a phase space like this, QP, right? Because we often draw, suppose this is an x variable, we have the x-axis to the right and the velocity up like so. That's the way it's done in physics, okay? And again, during my PhD work in the 90s, I worked with mathematicians, and they're kind of looking at this and saying, you know, wait a minute, I'm really not so interested in your history. It just, P comes before Q in the alphabet. I'm putting P to the right. So they would alphabetize. They have their P's going to the right and the Q going straight up. So you got to learn to live with that. We're going to see that Hamilton's equations give you a vector field. Okay, so this is what we call phase space. Okay, obviously it's very similar in structure to the classical state space. We're going to see that Hamilton's equations give us a vector field, and it swirls around like this. And this is kind of impressions. I have to go fast because we're running out of time here. The vectors get smaller as you go to the origin. All right, it's a very nice, well-behaved vector field. Yeah, I think we'll just have to call it good like this. So the evolution of the system in phase space is governed by this vector field, and we're going to be investigating this vector field. Okay, so how can we work out the equations of motion? All right, so the equations of motion we're going to see are the following: the EOM. So in other words, how do you actually use the Hamiltonian formulation? So 1 degree of freedom . Okay. This is true for the case of 1 degree of freedom. And again, for 1 degree of freedom, you don't need the subscripts. There's only 1 degree of freedom, so it's just Q for the single generalized coordinate, and the canonically conjugate momentum here is P. So these are the equations of motion, and there are several things to be said here. We want to appreciate the structure. Notice the right-hand side is just a function of Q and P. So this has the structure of a vector field on phase space. Okay, it's a vector field on phase space, and I want to emphasize, since the Hamiltonian is a function of Q comma P, and we've got some partial derivatives here, the right-hand side is just a function of Q and P. So it's a vector field, of course. It keeps on going. All of the phase space here, I can draw more and more arrows, like so. And so mathematicians are fond of speaking of the Hamiltonian flow. Like a vector field like this, they would speak of the flow. Now, if you look at the corresponding discussion in Lagrangian formulation, we would have a state space. So I'll emphasize it here with the cursive H for the Hamiltonian formulation, like so. Okay. In the Lagrangian formulation, this is going to be a little disappointing because it's the same picture. All right. So we're going to have to look at more complicated problems to see any sort of meaningful difference. In the Lagrangian formulation, we would talk about a Q axis like so, a Q dot axis. This is the classical state space. Okay. And again, same vectors. Can I quickly sketch this thing? I'm going to, let's see if I can do justice. I'm drawing vectors as fast as I possibly can here because every minute is precious. Yep, same picture. So again, the situation seems to be that there's some redundancy. This Hamiltonian formulation seems to have given us a picture that is identical to the original formulation in terms of Lagrangian mechanics. So what we're going to do in the coming lectures, we'll look at some examples where there's a marked difference between the Hamiltonian and Lagrangian formulation. For this problem here, the simple harmonic oscillator, it appears to be redundant, right? And obviously that's disappointing. But there are lots of interesting problems where you get a fundamentally different structure in the Hamiltonian formulation. Okay, so I promise you lots of interesting Hamiltonian stuff, including my friends in the laser industry. Yeah, people in Silicon Valley bringing home the big paychecks using Hamiltonian formulations of optics, right? You can have Hamiltonian formulations of optics. Okay, and with that, we're gonna stop recording and I'll stay here for questions. So I click on this stop.